This is second part of the class of this week. We will continue the chapter 1 basic concept. In this part, I'm going to talk about redistribution of stresses. Okay, redistribution of stresses. I will talk about several examples for you to understand the concept of plastic analysis and design. In the previous slide, we already talked about the behavior of the materials and the idealized curve, stress strain curve that we will use in the plastic analysis and design. And this part, I will talk about several very simple examples on how to apply the idealized curve in plastic analysis and design. The first example will be a place with a hole, and the second example will be a hot roll section with residual stress, and the third problem is 3-bar structure. And then homework will be provided. First, a place with a hole. Let's consider a steel plate with a hole, as you can see in this figure. Okay, this is steel plate. Okay, steel plate with a hole at the center, a hole at the center, under the tension condition. Okay, under tension condition. In the elastic analysis, okay, so you have to find out the location having highest stress. Okay, where is the location of highest stress? So as you know here, this point has a highest stress. Okay, so if it is load, then stress here have a diagram like this. So this point is highest stress, and in this side they are similar. Okay, similar, and the highest stress occur at this point. So stress here is 3 times of the average stress in the whole section. So sigma 0 means the average stress. So P divided by the area, and we have sigma 0. And the stress at this point, as you know, 3 times of the average stress. So in elastic analysis, for elastic design, okay, we can calculate. In elastic design, we use allowable stress concept. Okay, do you remember? You already know. In elastic design, we use allowable stress concept. It means the highest stress should not be exceeds sigma W. Sigma W means allowable stress in elastic design. And in design code, we already know the allowed stress equal to 0.6 of sigma y. Do you remember sigma y? Sigma y is the yielding stress, and allowed stress equal to 0.6 of sigma y. So it means sigma 0 equal to 0.2 sigma y. Then we have P0. P0 here is elastic limit load. Okay, elastic limit load. P0 equal to 0.2 sigma y multiplied by A net. What is A net? A net is the net area of this section. Okay, net area means the area of the section excluding the whole. So only area of this part plus area of this part, then that is net area. Okay, it is whole area. Okay, but it is net area. We don't consider the area of the whole. That is net area. So P0 equal to 0.2 sigma y multiplied by net area. That is elastic limit load. And I think you already know. It's simple for you. In plastic design, now we are moving to plastic design. In plastic design, this is the elastic stress diagram in elastic. So this point is yielding point or elastic limit. Okay, elastic limit. If the load is increased, then the elastic zone is increased. As I already mentioned that if the load is increased, then the stress is not increased anymore. It's based on the idealized curve. Okay. So this part is elastic part, and this part is plastic part. So if keep increasing the load, then the stress curve will be splitting like this, and finally we have fully plastic. So this is fully plastic. Okay, fully plastic. So in plastic analysis, yielding stress is reached in whole section due to the splitting of plasticity. Okay, the whole section is yield, or the yielding stress is reached on the whole section. That is plastic analysis. So now, very simple. The peak collapse equal to A net multiplied by sigma y. Right? It's simple. However, in plastic design, a safety factor is used. Okay, a safety factor. So let's say 1.7 is safety factor. So P0 here means plastic limit load. Plastic limit load. Okay, equal to peak collapse divided by 1.7, or equal to A net sigma y divided by 1.7, and finally we have 0.58 sigma y net. That is plastic limit load. Okay, plastic limit load. So I will show you the comparison between elastic and plastic design. In elastic limit load, we have PE mean elastic limit load equal to sigma y A net divided by K equal to 0.2 sigma y A net. What is K? K here should be equal to 5. It is stress concentration factor. Okay, stress concentration concentration factor due to the hole, okay, due to the hole of the end at the center of the plate. In plastic limit load, we have PP. PP means plastic limit load equal to P collapse divided 1.7. I already mentioned. Here, lambda equal to 1.7 is load factor for plastic design or steel structure under gravity load. Okay, so remember, lambda equal to 1.7 will be applied for all plastic design or steel structure under gravity load. The second example is a whole hot roll section with resistance stress. Let's consider a whole hot roll section like this. So here is hot roll section. Okay. In the hot roll section, there is a resistance stress due to the factoring procedure. So it means without any load application, okay, no load, but there is a resistance stress exists inside the section. So now this is column under action force. Then we will you can see what is the relationship between the load and the deflection, okay, in the hot roll section. Okay, so here in a resistance stress in the web and a little bit here in the flank, the resistance stress is tension, but this part of the flank, it is compression. So under compression, now we will consider the column under compression, so we don't need to consider the tension. Okay. Stress in the flank, only flank can be considered because in the web it will be similar to this part of flank, so we don't need to consider the web. In the flank, in elastic phase, this is tension and this part is compression, and sigma here smaller than sigma y. It is elastic. Elastic limit. Okay, elastic limit. Here, this point, sigma equal to sigma y. That is limit state. And elastic plastic phase. Elastic plastic phase. This part is elastic, okay, but this part is plastic because sigma equal to sigma y. And the last one is fully plastic. The whole section, the whole flank is plastic. Sigma equal to sigma y. So now we have load deflection curve. Load deflection curve. It is load, okay, and it is deflection. Then it's the first phase. We have elastic, okay, and this point is elastic limit or Elim point. From here to here is elastic, plastic, and from this point, it is full plastic or plastic collapse load. Okay, so this is plastic collapse load. Corresponding to this point is yielding load. Okay, or elastic limit load. Remember, plastic collapse load is not a fractal collapse, okay? And in the allowance stress design concept, P allow equal to 0.6 py in elastic design, okay? I already mentioned. And in plastic design, pp divided by 1.7 equal to p allowed for plastic design, and lambda equal to 1.7. I already mentioned, okay? So, you know, in the for the statical determinate structure, P allow equal to PW equal to P allow. But for the statically indeterminate structure, PWs may be higher than P allow. So it means in elastic design, it is conservative for indeterminate structure due to no considering of the force redistribution. Okay, so it is force deflection curve of the hot roll. The last example is 3-bar structure. Now we consider a 3-bar structure like this. This is a rigid bar, okay? It is held by 3 bar. The T1, and T1 has a length of L, and the T2 has a length of L over 2, the half of L. All bar has the same section of A, okay? And now we have to determine what is the relationship between P and D in the whole analysis, including elastic analysis and plastic analysis. What is relationship between P and theta? P and theta, load and deflection. Okay. What is relationship between load and deflection? Inelastic phase, inelastic. For equilibrium, we have 2T1 plus T2 equal to P, right? 2T1 plus 2T2 equal to P. That is equilibrium. Compatibility. It means the deflection in T1 should be equal to deflection in T2 and equal to theta. It means the deflection here is T1 L1 over AE should be equal to deflection in T2 L2 over AE. So from this one, we have T1 equal to T2 divided by 2, and T2 equal to P over 2. Okay, remember T2 equal to P over 2, or P equal to 2 times of T2, or P equal to T2 4 times of T1, okay, due to this equilibrium and compatibility. Initial yielding. Initial yielding means, as you know, the load, the force in the T2. The T2 will be yield first. So here is sigma y, and here is sigma 1. Sigma 1 smaller than sigma y. Okay, sigma 1 smaller than sigma y. It is initial yielding. Then corresponding to initial yielding phase, we have P equal to Py. It is P of initial yielding phase. what is T2? T2 equal to A sigma Y, okay, because T2 equal to T2 and Py equal to 2 times of T2. I already mentioned. It means equal to 2 times of A sigma Y. And that is force, okay, that is force. And how about deflection? The deflection delta Y equal to epsilon Y multiplied by L2 and equal to this one, okay. Elastic plastic phase. Elastic plastic phase means P greater than P2. This one is sigma Y, but this one sigma Y still smaller, sigma 1 smaller than sigma Y. Smaller than sigma Y. Then we have elastic plastic phase. Fully plastic phase, all of bar is under fully plastic. So we have sigma Y, sigma Y, sigma Y. Then what is P? PP equal to 3 times of A sigma Y. That is fully plastic collapse load. Okay. Then what is deflection? Deflection, dP equal to epsilon YL or equal to this one. Okay, so we have force and deflection. And now we have the load deflection curve. Load deflection curve. Load and deflection curve. As first phase, we have elastic, and this point is elastic limit. The load is Py equal to 2 times of A sigma Y, and the deflection is delta Y. From here to here is elastic plastic phase, and this point corresponding to fully plastic point. Okay, so PP plastic load equal to 3 times of A sigma Y, and the deflection is delta P. Do you remember delta P? You can check. And this part is fully plastic. Okay, or plastic collapse load. It is still sustain load with large deformation. Okay, so now we have a load deflection curve of the 3-bar structure. So I already provide you 3 examples regarding the plastic analysis. So now you understand how to apply the idealized stress strain curve of plastic material into the plastic analysis of very simple problems. And now I'm going to provide you more homework. So the homework of this part is problem P 1.2 in the textbook. So I already mentioned textbook, okay.